All right, section 5 is finally projectile motion. So, very important definition. The projectile is an object that's moving in two dimensions. So, we have that part, but it's under the influence of gravity and nothing else. So, we're kind of simplifying this a little bit. We're talking about just gravity. We're not including air resistance, drag, stuff like that. Only gravity is influencing this object as it flies through whatever in space. We can just say through whatever space it's in. Only gravity is influencing this thing. So examples: ball flying through the air, long jumpers when they make their jump, cars flying through the air in stunts, whatever. Okay, anything that's flying through the air. So real objects are also influenced by the air resistance. The effective air resistance is very small for something that's reasonably dense, moving at reasonable speeds. So for now, we're going to ignore air resistance. So as long as we can ignore it, any projectile will follow the same type of path. So it doesn't really matter what the projectile is. What we develop for one will work for others all the same. So the strategy that we see here will work for anything, as long as we could ignore the air resistance. So, moving on, we have in the diagram two different colored balls that are released at the same time. The red one falls straight down. The yellow one was kind of launched horizontally. Not kind of, it was launched horizontally. But because they're both technically projectiles under the influence of only gravity, we have normal free fall for one. The other one, because it was shot horizontally, has a horizontal component to its velocity, but also has free fall. So notice that the vertical motion for each is identical. So we have like a strobe going off or something in this, so that we can see the ball at certain moments in time. So we see the ball, the red ball 1, 2, 3, 4 times, and the yellow ball 1, 2, 3, 4 times. And at that moment, they're both at that line. We see each ball again 2 more times, and at that moment, they're both at that line. We see both balls here and here, and then both right there. Okay? So you can see that they are both falling at the same rate. Even though one was just dropped and the other one was launched horizontally, gravity is still pulling them both toward Earth at the same rate, which means vertically they are both falling at the same pace, let's say. Okay? So now the other important point here, let me use a vertical line. I'm going to draw vertical lines here so I can be a little bit more precise. Very important point. I'm just going to go from this one. I'm going to try to make these as vertical as I can. That's not vertical. So that's pretty good. That's pretty good. That's pretty good. All right, reasonable. Now, what we want to notice here is that the distance between each of these, so like this distance, this distance, this distance, these distances between the ball horizontally is revealing uniform motion. The ball is continuing horizontally as if it is not falling, okay? As if it was like rolling along a table or something, if we just look at the horizontal motion. So what we see here is that the ball, the yellow ball, is falling as if it was in free fall, vertically. But, so I'm answering this question at the bottom. Falling as if it is in free fall, because it is vertically. But vertically, yes. Now horizontally, what's it doing? it's basically moving horizontally. I don't want to say rolling because it's not really, but we can think of it as like rolling on a table. Moving horizontally as if it's rolling. But it's not really rolling, right? It's just like as if it was rolling on the ground in uniform motion, okay? So we have free fall and we have uniform motion. Going on simultaneously for this object that is flying through the air as a projectile. So this is very important. We're going to analyze both parts of the motion. Horizontal motion is uniform motion, and vertical motion is free fall motion. We have to analyze both. So, two balls are rolling toward the edge of a table, with one ball rolling twice as fast as ball two. So ball one rolling twice as fast as ball two. Both leave the table edge at the same time. So let me draw a little table here. It's going to be an amazing table. And here we are. It's like a giant pi symbol. Okay, ball one and ball two leave the table at exactly the same time, right? So ball one will be the green ball. So it rolls off the table. Great. But ball two is rolling twice as fast as ball one. So it's going to fall, we just saw, at exactly the same rate as ball one. Ball two rolls off, but it's moving faster. So logically, and if you did the lab, it will go farther. They fall at exactly the same rate. So like if I did the little snapshots like we just saw in the previous one, we would see these balls lining up as they fall, and eventually they will hit the ground. How? Which ball hits the ground first? Oh, they both hit the same time. Because they fall at the same rate. They will hit the ground at the same time. Their vertical motion is just like free fall. Which ball goes farther? So this is the one that's moving faster. It will go farther because they both hit the ground at the same time. One is going faster than the other, therefore the one that's going faster is going to go farther before it hits the ground. So which one was going faster? Ball one rolling twice as fast as ball two. Oh, so I have these colors completely backwards here. Let me fix that. Luckily for me, it's very easy to fix. Ball one is actually this guy, and ball two, if I can get the color right, ball one is rolling twice as fast as ball two. So now the colors are right, and we have ball one goes farther. There. Because it's going faster. So, good enough on that. Now, a projectile is launched at a speed of 22.0 meters per second at an angle of 63 degrees from the horizontal. First, we got to sketch the situation, so we'll do that. So, first thing I want to do then is set up axes that will act as my ground and my vertical. So this is going to be the x direction, positive x, positive y. And then the origin is going to be where I launched the thing from, whatever it was. Doesn't really matter. It's a projectile. That's what matters. So now we're going to launch at an angle of 63 degrees from the horizontal. So, okay, 63 degrees, probably something like this. All right, so that's 63 degrees. And that's going to be at a speed of 22 meters per second. So this is 22 meters per second, 22.0 meters per second. Okay, fantastic. Now what we want to do is we made the sketch of the situation, but we're not done yet. We haven't included the horizontal and vertical components of the velocity. So we're going to break this thing into components. And the question is just how exactly do you want to do that? Definitely we want to break x component along the x-axis, And now the question is, do we want to make a right triangle like that and make the y component up from the end of the x? Or do we want to break and put the y component like that? So this would be, if this is called v, if the vector is called v, we better label it. This would be v. Then we would call this v sub x, and this would be v sub y. But remember that the v sub y would also be over here, v sub y. Okay? It just depends on how you want to break those components and label them on your drawing. So now we've created a right triangle here, and we should figure out what the components actually are. So because the 63 degrees is sitting there as my reference angle, if I want to find out what v sub x is, that's my adjacent side. So my v sub x will then be, I would need adjacent and hypotenuse is what I know, so cosine of my angle equals v sub x over the hypotenuse, which is v. So then solve for v sub x, v cosine theta, cosine theta, and now I can plug in my stuff. I know 22.0 meters per second, cosine the angle 63 degrees. Make sure you're in degree mode on your calculator, so v sub x equals, and then we would use significant figures. We have 3 by the 22.0, so that's going to give us 9.99, probably 10.0 meters per second. Okay, so then v sub y. If I want v sub y, notice if I write it over here, it's opposite the 63 degrees. So that makes opposite and hypotenuse is what I know. So I'm going to go with sine this time. Sine theta equals v sub y over v. Again, multiply both sides by v. I have v sub y equals, and I just plug everything in. I have 22.0 meters per second times the sine of 63 degrees. And when we plug all that in, we get 19.6 meters per second. Okay, now check to see if this makes sense. V sub y should be less than 22, but more than v sub x, and that's exactly what we got. So we're good. We have everything figured out, and we're done. Okay, so that's how that goes. Now, lots to look at here. So the figure shows the velocity vector and its components shown every 1 second. So we see at the start here, 1 second later, 1 second later, 1 second later, 1 second later. Okay. Because there's no horizontal acceleration, so a in the x direction is 0, the value v sub x never changes. So if we look at that, v sub x is 10, 10, 10, 10, 10. It never changed the whole time. It's uniform motion in the x direction. So let me get rid of that so that I'm not confusing you. We saw it, we're good. Now, v sub y decreases by 9.8 meters per second every second. That's what acceleration talks about. Acceleration in the y direction is negative 9.8 meters per second squared. So in the y direction, every second that goes by, you're going to lose 9.8 meters per second. So in this example, we started off at 19.6. 1 second later, we should be 9.8 less than that. So 19.6 minus 9.8 is 9.8. Minus 9.8, and look right here. We have no vertical component anymore. The velocity in the y direction is 0. 1 second later, we subtract 9.8 from 0, we get negative 9.8. 1 second later, we subtract 9.8 from negative 9.8, and we get negative 19.6. So that is why the velocity component in the y direction is what it is every second that goes by. It's because of this acceleration telling us that every second that goes by, we're going to lose 9.8 meters per second. Okay? So, let me get rid of those. All right. Now, Projectile motion, I'm down here now. Projectile motion is therefore made up of two independent motions. I talked about this already. Uniform motion at constant velocity in the horizontal direction. We're moving horizontally, that's uniform motion, just like rolling on the surface of a table. Free fall motion in the vertical direction. That's free fall motion, we were talking about that earlier. They are independent of each other, which means we can use the equations for both. Horizontal motion, uniform motion in the x direction. We can use the free fall motion equations that we already have in the vertical direction. They are independent of each other, but we have to analyze them together to be able to solve these problems. So we will do both, and usually what's going to happen is we're looking for the delta t. That's going to be the common link between the two problems once we get going on these things. So, here are the kinematic equations for projectile motion. These are constant acceleration motion vertically, in other words, free fall, and constant velocity motion horizontally, in other words, uniform motion. So we have vertical motion, free fall problems over here. These guys are your buddies for the y direction. Velocity y final equals velocity y initial minus g delta t. That g, remember, is this. And it's a minus sign right here because g is actually positive 9.8. Okay? Now, we also have the position equation. Y final equals y initial plus vy initial delta t minus 1/2 g delta t squared. Again, the minus sign here because we're talking about g, which is actually positive 9.8. We also have the components. These guys right here we find by using trig. So set up your triangle, look at your reference angle, and then figure out what your trig is going to lead you to. Now, the horizontal motion, the uniform motion. We have velocity in the x direction final equals velocity in the x direction initial. In other words, it's a constant velocity. You do not change your velocity in the x direction. We also have x final, your position equation, equals x initial, where you started from, plus v sub x I, your initial velocity, which is the same as your final velocity, right? So we don't even need the initial letter there, but also delta t. So notice that we have delta t, delta t, delta t, and then over here delta t. Your link is delta t in all of those equations. Okay, and that's what it's talking about right here. The two equations are linked by the time interval delta t. If you don't know delta t, you're going to have to use both horizontal motion and vertical motion together, probably with substitution in some way to figure out what the answer is going to be. You may not ever even know what delta t is. It's possible. So be aware. Okay. One more thing and we're done with this section. 100-gram ball rolls off a table and lands 2 meters from the base of the table. A 200-gram ball rolls off the same table with the same speed. How far does it land from the base of the table? Think about it. Think about the concept. It's a 100-gram ball versus a 200-gram ball. The question you got to ask yourself is, does the mass here matter? We're talking about free fall versus uniform motion. Free fall in the vertical direction, uniform motion in the horizontal direction. They have the same table, which means they fall from the same height. This one lands 2 meters from the base of the table, but they both went off with the same speed. So how far does the other one land from the base of the table? What is your time for the other one to hit the ground? Well, it's the same time because everything falls at the same rate. It doesn't matter what the mass is. So if they went off at the same speed, they're going to hit the ground at the same time and in the same place. The answer is 2 meters. So hopefully you got that one right. That is the entire